Hey there, so this is our unit on chemical reactions. There's several chemical reactions that we're going to learn about and learn to balance and learn to predict. We're going to use a couple of tables and we're going to have to memorize some solubility rules, which is not that hard, but you can do it. So we're going to balance chemical equations, write balanced chemical equations from word equations. So it's kind of like the chemistry version of a math word problem. And we're going to identify and predict products for the main types of chemical reactions, which 5 types is what you'll learn, and we'll be able to predict products for those 5 types of chemical reactions. So today we're going to learn what the chemical reaction is, talk about the law of conservation of mass, and start balancing some chemical equations, which most of you have been able to balance equations since 8th grade. It's just been a while, so I'm pretty sure this will come back to you pretty quickly. Different parts of the chemical reaction, we have reactants that are going to be on the left and products that are going to be on the right. Reactants are kind of like the ingredients in a cake, and the products would be the cake. So reactants undergo some sort of chemical change. They're written on the left-hand side of this arrow. This arrow is called a yield sign, and it's what we start with. The products, or the new substance that's going to be produced, is written on the right of the yield sign. Different chemical symbols that we're going to use, and we're not going to use all of these, but it's worth taking a look at. The plus sign separates reactants or separates products. It's what's added to each other on a reactant side, or what's produced. If there are 2 or more products on the product side. Like I said, the arrow is a yield sign. This little triangle here over the yield sign indicates that heat has been added. A chemical formula above the yield sign would indicate that a catalyst has been added, and this one down here is a reversible reaction, or a reversible reaction. Most chemical reactions, though, are reversible until they reach equilibrium. S stands for solid. L, that's an L, cursive L, stands for liquid. G stands for gas, which all of these are probably pretty obvious. AQ is the one that you haven't seen before, and you're going to use that a whole lot during this unit. AQ means that something has been dissolved in water. So think aqua. Something's been dissolved in water. How do we know that a chemical reaction has taken place? Well, some evidence, some indications that reaction has taken place. There may be heat or heat given off, or absorption of heat, which actually would make it feel cold. It would be absorbing heat from surroundings, so the chemical reaction might feel cold. There may be light produced. There may be production of a gas, like in the form of bubbles. You would see bubbles. There may be a precipitate form, a solid formation of a precipitate. There may be a solid formed from 2 liquids, and it would be a fairly obvious change. That precipitate would generally float and sink to the bottom. There may be a change in color or a change in odor. Those things indicate that a chemical reaction is taking place. The law of conservation of mass says that mass can't be created or destroyed in an ordinary chemical or physical change, which is what we're talking about. Mass of the reactants is always equal to the mass of the products. That's the big takeaway here. Whatever mass of reactants you have, the mass of the products must be equal. So looking at this problem for the law of conservation of mass, how much zinc was originally present in the zinc carbonate? So here we have calcium and zinc carbonate being added together in the reactant. Okay. Over here in the product, we have calcium carbonate plus some zinc. So what I want to know, how much zinc was left over? Well, law of conservation of mass says that what you start with, you have to end with. So if 64 plus 192 is added together, then 152 plus something would have to equal. So 64 plus 192 is equal to 256 grams of reactant, which means that 256 grams of 256 grams of product must be left over. Well, the calcium carbonate is only 152. So if you add these 2 together and you subtract the 152, that'll give you your mass of zinc, which is 104 grams. So chemical equations can be written in 3 different ways. You can write a word equation, which is my favorite, but you're not going to like it as much. So it tells you exactly what's going on. Solid sodium, okay, that's just Na, solid sodium, combines with oxygen gas. So in my mind, I see Na plus, because it's combining, oxygen gas is O2. Remember the Brinkelhoff atoms. Oxygen is O2. And it says that it yields a sodium oxide solid. So I draw my arrow sign, and then Na2O would be my sodium oxide solid. So that's one way that you might see a chemical equation. You also will see a skeleton equation here. A skeleton equation is simply an unbalanced equation. You just write whatever's in the word equation. So there's my solid sodium plus my oxygen gas yields Na2O. Okay, that's unbalanced, so it's a skeleton equation. Balanced equation is the final portion where you balance all the atoms. 4 sodiums. See, up here in the skeleton equation, there's 1 sodium, but there's 2 sodiums in the product. And remember, law of conservation of mass says that we have to have the same amount of mass on either side. So if you have 1 sodium here and 2 here, those have to be equal. And if you have 2 oxygens in the reactant and 1 in the product, that has to be equal. So that's why we balance the equation. Here, after you balance the equation, 4 sodiums, 2 times 2 is 4 sodiums. 2 oxygens here, that coefficient of 2 gets multiplied by not only the sodium, but also the oxygen. So that would give me 2 oxygens in the product. The law of conservation of mass, equations have to be balanced because atoms can't be created or destroyed in an ordinary chemical reaction. So there must be the same number of atoms on both sides of the equation. That's why we're balancing them in the way that we are. So balancing chemical equations, there's a couple of different numbers that you have to be aware of. Subscripts are the number of atoms of each element. Subscripts are the numbers that are lower in the chemical formula. So here I have an example of an equation that we're going to balance. That is a subscript. That is a subscript. That's actually 2, but that's a subscript. That's a subscript. Coefficient is the number of molecules. Coefficient is a number that we are going to use to balance chemical equations. You can never, ever, ever change the subscripts. What you can change to balance an equation, though, are the coefficients. Okay, so that's what we're going to use, coefficients. So tips for balancing. Just some generic tips. They usually work, but not always. But just to get started, balance the metals first, then balance nonmetals. Just a tip. Balance oxygens and hydrogens last. Okay, I can't stress that enough. Oxygens and hydrogens will most often work themselves out if you balance everything else first. They can be kind of a pain to balance, so you definitely want to do them last. Reduce all coefficients to the lowest whole number ratio. So if all of the coefficients can be reduced, you have to do that. Don't forget, balance only by changing coefficients, never ever subscripts. So here's our first balancing example. This is what I have here. I have H2 plus O2 yields H2O. So that's hydrogen gas plus oxygen gas is going to make some water. Well, I have 2 hydrogens here, and I have 2 hydrogens in the product. So those hydrogens are balanced. Oxygens aren't. There are 2 oxygens here, but only 1 in the product. So that has to be balanced. And remember, all you can use are those coefficients. So if I have 2 here, I'm going to use a coefficient of 2 right here, because that 2 will get multiplied by the hydrogen and by the number of oxygens, giving me 2 oxygens in each side. But what happened? Well, we messed up our hydrogens. I now have 4 hydrogens in the product. So I go back over here. So there are 2 hydrogens here. So I know that if I multiply by 2, I'll have 2 hydrogens in the reactant also. So I have 2 hydrogens plus, there's my 2 oxygens, yields 2 water molecules. Okay? But they balance. 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. All right, so let's balance this other one. So SO2, so I have 1 sulfur in the reactant, I have 1 in the product. So sulfurs are good. I have 2 plus 2 oxygens. If the atoms are on the same side of the yield sign, you have to add them together. Okay? So that means I have 4 oxygens in the reactant, but only 3 in the product. Well, it's always a problem if you have an odd number on one of the sides, okay? So I like to even that up. The easiest, quickest way to even up an odd number is to multiply by 2, and we just see how that works out. So I now have 6 oxygens in my product. Well, over here I have 4 oxygens in my product. But look, if I do 4 oxygens plus 2, how many is that? Well, that's 6. So my oxygens are now balanced, and what happened? Also balanced my sulfur. So the balanced equation would be 2 SO2s, 2 sulfur dioxide plus my oxygen yields 2 sulfur trioxides. Okay, 2 sulfur, 4 plus 2, 6 oxygens. 2 times 3, 6 oxygens. We're balanced. Okay, that next problem, let me put that up here. I printed them all off for you so you can see them. So our next balancing example. Okay, it looks longer, but don't panic. Just because the equation looks longer doesn't mean that it's more complicated. It's the same stuff. Okay, I have 1 sodium in my reactant, 1 sodium in my product. So sodiums are good. Okay, go to the next metal. There's calcium. Calcium's a metal. 1 calcium, 1 calcium. That 2 only applies to the O, the oxygen, and the hydrogen. Okay, so it doesn't apply to the calcium. So calciums are balanced. Okay, remember to balance hydrogens and oxygens last, so I go to bromine. I have 2 bromine in my reactant, 1 bromine in my product. So that's an easy fix. I use a coefficient of 2. That would give me 2 bromines. Now my bromines are balanced. But look what happened. The sodium got messed up. All right, so I'm going to go back over here and use a coefficient of 2 to balance my sodiums out. Then, let's see, now all we have left are the oxygens and hydrogens. So this is 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. It's balanced. So 2 sodium hydroxides plus calcium bromide yields calcium hydroxide plus 2 sodium bromides. Okay? Just because it's longer doesn't mean that it's more difficult. All right, so let's look at this one. Remember, we're going to balance metals first. So we'll start with potassium because it's first. There's 2 potassiums here, 1 potassium here. So let's balance that up. Put a 2 there. So potassiums are good. If the polyatomic ions are the same on either side and haven't been broken apart, you can balance them as a group. So I like to do that. So I'm going to put parentheses around my polyatomic ions. I have 1 chromate. Okay, there's no subscript here, so 1. So I have 1 chromate. Over here I have 1 chromate. Okay, so I don't need to balance that. Chromates are balanced. 1 lead, 1 lead. 2 nitrates, 2 NO3s. Over here I have 2 NO3s because remember that 2 applies to not only the potassium but also that nitrate. So it's balanced just with that 2. Okay, 2 CrO4. Remember how I told you should always put parentheses around your polyatomic ions if you're in my class? Well, this is why. Okay, this is where it helps you out when you're balancing chemical equations. Oh, not B, PB. PB, lead, chromate. Balanced. Okay, so here's a word problem. Let's work on the word problems here. Carbon monoxide gas reacts with oxygen gas to produce carbon dioxide gas. Okay, so we're not going to panic when we have word problems. We're just going to take it a teeny piece at a time. Carbon monoxide gas reacts with, so what is that? That means plus. Reacts with oxygen gas to produce carbon dioxide gas. Okay, so first part, carbon monoxide gas. Carbon monoxide is CO, and it's a gas. says that it reacts with, so there goes my plus, oxygen gas. You know what that is, it's O2. To produce, next I write my arrow, my yield sign. To produce carbon dioxide gas, you know what that is too, CO2. Okay? Now we need to balance one carbon, check. See, 1 plus 2, 3 oxygens, 2 oxygens. That's a problem. Remember, you don't like on odd numbers. So over here I'm going to even this up by putting a 2 there. Now I have 4 oxygens in my reactant and 2 carbons. So I'll put a 2 there, and look what happened. I balanced. 2 carbon, 2 carbon. 4 oxygens, 2 plus 2, 4 oxygens. So I'm balanced now. Solid carbon reacts with solid sulfur to produce solid carbon disulfide. You can do that. So solid carbon would be carbon with an S next to it. Reacts with solid sulfur. So far so good, pretty easy. To produce, there goes my arrow, solid carbon disulfide. Carbon, 2 sulfurs, carbon disulfide. Okay, so I can balance that now. There's 2 sulfurs, 2 sulfurs. Okay, that's it. That's it. It's balanced. Some of them are easier than others. All right, do some more practice here with word problems. Solid potassium. There we go. Get it all on the screen for you. Solid potassium chlorate decomposes to yield solid potassium chloride and oxygen gas. So solid potassium chlorate decomposes. Okay, this is a decomposition reaction. It decomposes. Oh, we're not there yet. Yep, solid potassium chlorate decomposes to yield solid potassium chloride and oxygen gas. Sorry about that. Broke my pencil. Had to get another one. So let's see. We're going to go ahead and balance this one, or write it all out. So solid potassium chlorate. Potassium and chlorate, look it up on your list, ClO3. That's plus 1, that's minus 1. So you can write that, solid potassium chlorate. Decomposes to yield. Okay, well there's no other reactants, so there's my yield sign. To yield solid potassium chloride, plus 1, minus 1, no subscripts, and oxygen gas. Should have put my phase symbols there. It's S and S. There we go. So let's see. This looks complicated, but it's not. 1 potassium, 1 potassium. 1 chlorine, because there's no subscript out here. 1 chlorine. That 3 only belongs to the oxygen. 1 chlorine here. 3 oxygens, 2 oxygens. So remember, we don't like odd numbers, so we're going to put a 2 right there. That would give me 6 oxygens. I'm going to go ahead and balance that one out. 3 times 2 is 6 oxygens. Now, my potassium and my chlorine have both, I have 2 of each in the reactant, so I'm going to put a coefficient of 2 there and balance in the product. So 2 potassium, 2 potassium. 2 chlorines, 2 chlorines. 6 oxygens, 2 times 3. 3 times 2 is 6 oxygens. So we're good to go. Solid iron reacts with gaseous chlorine to produce solid iron 3 chloride. So my solid iron right here, solid iron is just Fe. And I'm going to put a phase symbol right there for solid. It reacts with, so there's my plus, gaseous chlorine. Remember, chlorine is a Brinkelhoff atom, so it gets a subscript of 2. It says that it produces solid iron 3 chloride. Can you write that formula? Iron 3. So iron is Fe with a plus 3 oxidation number, because that's what that means. Chlorine is Cl minus 1. So crisscross those, use them as subscripts, and that would be FeCl3. Let me take those off. We don't need them anymore. All right, so now we can balance the equation. iron, 1 iron, 1 iron. 2 chlorines, yeesh, 3 chlorines. Told you we don't like odd numbers, so I'm going to multiply by 2. So that'll give me 6 chlorines. No longer an odd number, it's an even number. That I can work with. So I go back over here. 2 times what gives me 6? 3. So my chlorines are balanced. I have 6 here and 6 here. 2 irons, though, I'm going to use a coefficient of 2, and my irons will be balanced. So yeah, there's another word problem for you. Okay, we'll work through those. It's okay. Oh, my slide is not advancing. Okay, got my slide to advance. There are 5 general types of reactions, like I told you in the beginning, that we're going to learn about. Synthesis, decomposition, single replacement, double replacement, and combustion. So there are 5 different reaction types. Some are more complicated than others, but we'll work through them all. Okay, so what I want you to do is pause me and balance those equations. And then I want you to think about, what do they have in common? Okay, so if you balanced these equations and you decided, you looked and said, well, what do they have in common? Well, it looks like for each one of these, there are 2 reactants and 1 product. Okay, 2 reactants and 1 product. All of them have 2 reactants and 1 product. That's what they have in common. Synthesis is the type of reaction that one is. It's a combination of 2 or more substances that forms a single compound. It usually looks like this. There will be some element plus some element, and there will always only be 1 product. Okay? Example here, hydrogen plus oxygen makes the 1 product of water. Okay? And you can draw anything you want to for that graphical representation. However, you can see in your mind 1 plus 1 equals 2. However you want to do that. So if you want to draw a graphical representation, go ahead and do that. We're going to predict the products of the following synthesis reactions. So we'll see what a synthesis reaction actually looks like. Okay, let's do that. Let me get that under my document camera. There we go. All right, so aluminum and chlorine. So we're going to predict the products of this synthesis reaction. Aluminum and chlorine. Those are the reactants. I've just given you the reactants, and you're going to have to figure out the products. So aluminum is Al, and you're adding it to chlorine. Remember, chlorine is a Brinkelhoff atom. So 2 things will make 1 thing. Okay, what could aluminum plus chlorine possibly make? Okay, well, it can't make lead sulfate. Duh. It can only make aluminum chloride. Right? You're adding these 2 together. The only thing it can make is a compound that has these 2 atoms in it. So once you make that compound, once you put those together, you have to check and do the subscripts right. So aluminum's oxidation is always plus 3. Chlorine's oxidation number is -1. When you crisscross those, you get AlCl3. So that's the next step. Once you figure out what that product's going to be, you have to write the subscripts correctly for the new product, for the new compound. When we're done with that, you can balance the equation. 2 chlorines and 3 chlorines. I'm going to even that out to give me 6 chlorines. So I'm going to put a 3 here, 6 chlorines and 6 chlorines. 2 aluminums, 2 aluminums. So I'm balanced. All right, so the next one, solid zinc and solid iodine. Don't let these things weird you out. Don't let solids weird you out. You're adding zinc and iodine. So you put zinc, you can put the face symbol of solid, plus iodine. Iodine's a Brinkelhoff atom. And put the S. When you add those 2 together, when you shove zinc and iodine together, the only thing they can make is zinc iodide. Check oxidation numbers on this compound you just made. Zinc is always what? How about iodine? Crisscross, CnI2. Okay, I'm going to erase my oxidation numbers up here now. And what do I have? I have 1 zinc, 2 iodines, 2 iodines. This one's already balanced. You don't have to do anything to it. Happy day. We like that. Okay, so some more skeleton equations. Okay, balance these and then think about what they have in common. Go ahead and pause me for a sec. Okay, what these have in common, there is one single reactant and two or more products. Okay, these have been broken down into their pieces. Okay, what is that? That's a decomposition reaction. A single compound is broken down into two or more products. It's kind of the opposite of synthesis. Most decomposition reactions require energy in the form of heat, light, or electricity. Here we have the opposite of what we showed you in the synthesis reaction example. Water, using some electricity, can be broken down into hydrogen gas and oxygen gas. It can only be broken down into the pieces that it's made from. So don't start throwing weird atoms in there, because they're not there. All right. So the next one, lead 4 oxide. Let me get it here for you in the document camera. Okay, we're going to break this down. When you have a decomposition reaction, all you're going to have is a single reactant. Okay, there's no plus, nothing. Okay, just that single reactant. So lead 4 oxide. So let's write the formula for lead 4 oxide. Lead is Pb, and because of the 4 there, means it has a +4 oxidation number. Oxygen is always -2. When you crisscross those and use them as subscripts, Pb2O4, which that reduces. You can simplify these. Okay, both of these can be divided by 2, so they're going to need to be. So the correct formula for lead 4 oxide is actually PbO2. Here, let me erase that a little bit better for you. PbO2. So lead 4 oxide is my only reactant. Okay, it's my only reactant. So it has to be broken down. It's going to be broken down into its pieces. There are no other pieces other than lead and oxygen. So when you break this apart, okay, don't make it complicated. It breaks down into lead and O2. The reason it breaks down into O2 is because oxygen is a Brinkelhoff atom. Has zero to do with this. Nothing to do with this at all. Okay, this is from an oxidation number. This is because oxygen can't exist alone, and it's diatomic. So when we put the products, Pb plus O2, look, it's balanced already. All right, doesn't always work that way, but it did this time. So let's try sodium nitride. Okay, sodium nitride. Sodium is Na. Nitride is nitrogen with the ending changed. Sodium has an oxidation number of +1. Nitrogen -3. Crisscross and make them into subscripts. So let me erase those. It's Na3N. Okay, that is my only reactant. If that is my only reactant, you have a decomposition reaction. And it's going to break down into its pieces. It can only break down into Na plus N2. Remember, nitrogen is a Brinkelhoff atom. That's why it gets a subscript of 2. So now we can balance this equation. There are 3 sodiums, 1 nitrogen, but 2 over here. So I need to put a coefficient of 2. So what does that do? Yeah, that messes up my sodiums, but that's okay because I do all my work in pencil because I'm smart. I put a 6 there. And then what do you got? You have a balanced equation. 6 sodium, 2 nitrogen, 2 nitrogen. Okay, so we've got some skeleton equations here to balance. This is a different type of reaction. Okay, let me get my paper here. There you are. So let's balance these. These look complicated. These are, what would they have in common? So go ahead and pause me for a minute and balance these equations. Okay, so what they have in common, here, look. They both start with a hydrocarbon. Why is it a hydrocarbon? Because it's got hydrogen and carbon. CH, and there's a CH. No, the subscripts aren't the same, but they're both hydrocarbons. And we're adding oxygen, okay? What are the products? Products are exactly the same. In each reaction, you have carbon dioxide plus water. Carbon dioxide plus water, okay? So let's balance these reactions real quick. So 1 carbon, 4 hydrogens, 2 hydrogens. So I'm going to put a 2 there. So give me 4. How many oxygens are here? There's 2. And this is 2 plus 2. So there's 4 oxygens in the product. So I'll put a 2 there, and that equation would be balanced. Okay, this one's going to be a little bit more complicated. I have 2 carbons, 2 carbons, 6 hydrogens. Okay, well here I have 2, so I'm going to put a 3 there. 2 oxygens in the reactant. But look, I have 4 oxygens plus, whoa, that gives me an odd number. Odd numbers, no bueno. So we're going to erase our coefficients, okay? And we're going to do a little trick for these types of reactions. When you get an odd number over there, it is my advice that you always double your first carbon, okay? That just means put a coefficient of 2 right here. Even though you didn't really need it, trust me, it's going to work itself out because that'll even up the oxygens over here. Watch it work itself out. So I put the coefficient of 2 here, okay? 2 times 2 is 4. 4 carbons. 2 times 6 is 12 hydrogens. Well, 2 times 6 is 12 hydrogens. What's 4 times 2? Over here I have 8 oxygens plus 6 times 1, 6. How many? Look, I evened up my oxygens. So I have 14. Okay, I have 14 oxygens in the product, but 2 here. Well, what number times 2 gives me 14? Yup. Okay, this is a real complicated type of reaction, but if you double that first carbon, it'll work out for you every time. So those types of, equations are called combustion reactions. Combustion, commonly known as burning, okay, when a substance reacts with oxygen. That's why you had O2 in each of those combustion reactions. So what characteristics come with a combustion reaction other than a very predictable set of products? They're exothermic, usually. Heat is generated. Let's see, what else? They have the same setup. There will always be oxygen in the reactant. Why? Because you need oxygen to burn, to combust. The products of a hydrocarbon combustion reaction, see hydrocarbon, C's and H's, will be carbon dioxide and water every time. Now, other things can burn. I don't want you to think that only hydrocarbons can combust. Metals can also combust too. So we have metal combustion reactions. So the metal combustion reactions will have some sort of metal plus oxygen, because you need that to burn. And what that's always going to make is the metal oxide. It'll make whatever the metal is. It'll look just like a synthesis reaction, but it'll be a combustion reaction because you have that oxygen in the metal. So let's take a look at another one of those. So the combustion of magnesium. We're going to do that one. Okay, get that in the, make sure it's in your pane. Yeah, it is. So the combustion of magnesium. How do we know it's a combustion reaction? Well, it'll tell you it's a combustion reaction, or it'll say magnesium is burned or something like that. So magnesium is my metal, Mg. I need oxygen to burn, okay? So magnesium plus oxygen. This is the same setup. And remember, I told you the products are very predictable. It'll make a metal oxide. Well, is it going to make iron oxide? Well, no, because it's magnesium. So this thing is going to make magnesium oxide. Okay, then you need to check oxidation numbers on the new compound. That's +2 because it's in group 2. That's -2 because it's oxygen. Crisscross and reduce, and you just have MgO. All right, so I can balance from here. I have 2. See, I can't start with my metals because my metals are done. So I go to oxygen. 2 oxygens, 2 oxygens. That gives me 2 magnesiums in the product. Sorry. So I'll put 2 in the reactant. And there you go. Okay, combustion of magnesium. All right, so some tips for balancing combustion reactions with hydrocarbons. I told you they were hard, and I showed you that first one's kind of difficult. First, balance hydrogen atoms. If the coefficient that you add to the product side is odd, double it and add a coefficient on the left. Okay, I like to go with balancing carbon atoms first, okay, by doubling the carbon and then balance them. So let's see. Let's try these. That's just a tip. You can do it either way. So combustion of methane. All right, let's see if we can't get this in here. Okay, so we have the combustion of methane here. Okay, note up here, reactions with hydrocarbons, combustion reactions of hydrocarbons, carbon dioxide and water will always be the products. All right, so we've got the combustion of methane. That's my hydrocarbon, so I'll write that first. What do you need in order for something to burn? Well, you need to add oxygen. And the products will always be the same, CO2 and H2O. Okay, both of these hydrocarbon reactions are going to be exactly the same. Okay, the only difference is going to be the hydrocarbon that's used. So we could set this one up already. C4H10. There's my propane. There's my hydrocarbon. Same exact over here, exactly the same down here. So my hydrocarbon plus oxygen will make carbon dioxide and water. This works with hydrocarbon combustions, okay? You will always add oxygen to the reactant, and you will always get carbon dioxide and water each time. So let's balance this one. So the way I tell people to balance combustion reactions is you double the first carbon. What does that mean? That means double it. Put a 2 next to it. So that gives me 2 carbons in the reactant, 2 carbons in the product. Okay, my carbons are balanced. Then I'm going to balance my hydrogens. How many is that? 2 times 4 is what? 8? 2 times 4 is 8. Now in the product I have, remember you have to add the oxygens together. 2 times 2 is 4 oxygens plus 4 oxygens. So that's 8 oxygens in my product. 4 times 2, 8 oxygens in my reactant. Well, what do I need to do? Look here. These coefficients can be reduced or simplified. So I'm going to do that. 2 divided by 2 would be 1. You don't have to write a 1, but you can. 4 divided by 2 would give me 2. 2 divided by 2, 1 again. And 4 divided by 2, 2. Okay, so my equation's now balanced. 1 carbon, 1 carbon. 4 hydrogen, 4 hydrogen. 4 oxygen, 2 plus 2, 4 oxygens. So let's go down here and do the propane. I'm going to double the first carbon. I'm going to put a 2 there. 2 times 4 is 8. 8 carbons. 8 carbons. 8 carbons. So I go back over here and balance my hydrogens. 2 times 10 is what? 20? Okay, so go over here. Don't freak out. Don't worry about big numbers, especially in these hydrocarbon combustion reactions. So I have 20 there. So 10 times 2 would give me 20 hydrogens there. Now I need to count up my oxygens in the product. I have 2 times 8. What is that? 16 oxygens plus 10 times 1, 10 oxygens. What is that? 26? Yup, 26 oxygens. Well, look, that's a 2. So 26 divided by 2, right, 13 oxygens. So I'm not real sure you could come up with that easily on your own. My trick of doubling that first carbon and balancing everything off of that will work for you every time. The only thing that you might have to do is what we did here, reducing coefficients. Okay, so that's how to balance combustion reactions. You may need a little bit of help on those, but we can get you help if you need it. Okay, so that ends day 1, and we'll go on to a couple of other types of chemical reactions for day 2.